because we don't get, so most grants are instrumentation grants, right? Like chemistry, biology, whatever, physics, engineering, you get millions of dollars because you're trying to get equipment and instruments to go along with the grant. Mathematicians grants, by comparison, are, yeah, so like what else? So my grant has money in it for students, right? Most of the money in my grant is so that I can have student researchers, right? And travel money. So yeah, chalk and paper. I guess I could buy chalk and paper with my grant, but I get it from the department. So. All right. Okay. So we are going to embark on the other part of calculus now. So I posted homework on chapter 4. Chapter 4 homework is posted. And that covers Taylor polynomials. Stream values. I have yet to, but I'm going to post, for those of you that don't actually know how to, I don't expect anybody to do extreme value problems where you have to compute determinants by hand. So I have not posted yet, but I'll post. If you don't know how to do it, I'll show you how to get eigenvalues out of Wolfram alpha, which is very easy to do. There is, that's posted. And now we're going to do the other half of calculus, which is we're going to do integration in several variables. And I'm going to try to do my best. It's sort of hard to avoid like regurgitating some of the material that you guys learned in 241 for various reasons. Partly because 241 is extremely uneven in the way that the topics are presented. Part of it because a lot of you guys haven't taken 241 in years. Part of it because 241 is taught as a non-conceptual like set of algorithms for computing things that don't have a lot of meaning, right? So I'm going to do the best I can to try to take the theory of integration and give you some of the ideas about what's going on. You need to remember enough of the structure of how integrals work in 2 and 3 variables so that when we get to our actual, what we actually want to study, which is the Stokes theorem and Green's theorem and the Gauss theorem, that we can say something meaningful there. But to get there, we're going to have to talk about the theory of integrals. So I guess the first thing is, I like to ask these questions of you guys. What is an integral? Okay. So all right, so there we are. All right, so what is an integral? Okay, so Jack says it's a sum. What kind of sum? For loop. Essentially, yes. So yes, it's a sum and also a for loop. Area below. Okay, so you got a sum. I've got the answer for loop. I have the answer area below curve. Anything else it is? Antiderivative. Okay. Are any of these connected to each other? That's pretty disparate set of ideas here, right? I mean, a sum of some undetermined thing. Yep.
R is sum of the area.
Oh, all right. So yeah, that's Riemann is who you're talking about. Yeah. So it's a Riemann sum that approximates the area underneath the curve, and which you could compute in a computer with a for loop. So, which is, I mean, this is the way that a computer scientist actually does think about this. This is a for loop running over an index, right? So what is the Riemann, the idea of a Riemann sum, and the reason why the sum and the area below the curve correspond to each other is because the basic idea is you've got some function f of x, which is nice enough. And the idea is to take the domain of the function, say from A to B, and you cut it up into pieces, maybe evenly, maybe not evenly. And then you go up to the function and somehow you cut the function up into rectangles, right? However you do it, maybe you do an upper sum or a lower sum, it doesn't really matter. The idea is that the area of the sum of the area of the rectangles approximates the area under the curve. And then what do you do with it? You get this Riemann sum, right? So this idea of cutting is going to be sort of intrinsic to the way we're going to approach thinking about double and triple integrals here. So then what do you do with this picture? This approximates the area underneath the curve. What do you do with it? This, okay. So then you take a limit as maybe delta x goes to 0. So if you think about this as sort of delta x, if they're non-uniform, you just make sure that the maximum width goes to 0. And if you take the limit of this guy, the limit of this sum, what falls out the other side is this object that we call the definite integral. Okay, so all of that's related to each other. These dudes are all the same. Now, on the other hand, there's this idea of antiderivative. What we call, that's a different symbol. So there we're saying something like the integral of f is a function capital F if d by dx of f is equal to little f. It's the operation of undoing differentiation. So this symbol has no numbers on it. This is called the indefinite integral. And it represents anti-differentiation. So you guys have got pretty much what I'm interested in lifting up to the several variable case, which is integration has to do with cutting things into small pieces and then applying a limit to make the approximation become exact. And on the other hand, integration has to do with computing antiderivatives. So why are these the same? And for bonus points, who figured it out? Okay, so that's one half of the answer. Leibniz, there we go. And the theorem is fundamental theorem of calculus. It's called fundamental, so you should all remember it forever for the rest of your lives. As all things fundamental. Okay, so now I'm regurgitating stuff. I mean, I'm recapping stuff that you guys have all seen before, but there's something important about the fundamental theorem that I want to point out that is sort of where we're driving with all of this stuff. With the fundamental theorem of calculus, well, first off, there's two parts. So go ahead and hit me with part A and part B, or part 1 and part 2. I'm going to give you part 2, which is the one everyone thinks is the fundamental theorem of calculus, which is actually a consequence of part A. That's the part that says you can connect up the idea of antiderivatives with the idea of areas, right? That you compute the area underneath the function by taking an antiderivative and evaluating it on the endpoints of the interval you're working on. What's part A say? Okay, that says that integration and differentiation are inverse operations. This is why this is the one that comes first, right? Integrals and derivatives are inverse operations. And once you know that, then you can recover the definition of the relationship. I mean, this is the sort of thing you do forever without realizing how weird this is. This works in general. And this theorem is way weirder than you think. Because we're going to talk about this more. I'm going to motivate the study of integration here. But the basic idea is this says that I can figure out some quantity related to f by evaluating its antiderivative on the boundary of its domain. That's weird. I mean, that's a weird idea. You've got some function f, and it has a domain that runs from A to B. And we say somehow that this area underneath here, I calculate an antiderivative, and then I put in just the values on the boundary, and that somehow that recovers that area. So knowing what this function does on the boundary is enough to figure out what it did in between. So for those of you that at least vaguely remember Green's theorem and Stokes' theorem, Green's theorem and Stokes' theorem are the same kind of theorem, right? So what we're driving at is this relationship of the behavior of a function on its boundary to the behavior on the inside extends way beyond the fundamental theorem of calculus. So this relationship between boundary behavior and interior behavior, this is kind of where we're going with this, is what can we say about what would the fundamental theorem of calculus look like if we were working in functions of several variables instead, right? So ultimately the goal is, we're going to build a theory of integration, and then we're going to take a look at this theorem and figure out what happens for a function that looks like this, or a function that looks like this. What would the fundamental theorem of calculus look like in that case? This is kind of where we're going with it. If I have a vector field or a scalar field, can I also come up with something that looks like a fundamental theorem of calculus? Can I somehow meaningfully integrate a function like this by looking at its boundary? Okay, so this is kind of the long-term goal here is, what does the fundamental theorem of calculus look like in vector land? But to get there, we're going to have to rehash some of the existing theory, and I'm going to have to teach you change of variables for real, which you probably didn't do in your 241 class. All right, let's get started. So 5.1, chapter 5.1 is about, calls them multiple integrals. But I'm going to specify here what I mean by that. Really what 5.1 is about is something called iterated integrals. So the idea is, this is all motivated by the same idea that let us take a function and cut it up into a bunch of rectangles, and then approximate the function with the area of the rectangles. Right, that the idea that the area under F is about equal to the area of the slices. Yeah, I'm just destroying this chop today. So the idea of an iterated integral is pretty similar. We're going to start by thinking about integrals that look, or surfaces that look like this, right? So, oh man, these are hard to draw. How about a loaf? Can I draw a loaf of bread? That's a good question. Okay, so a loaf of bread kind of looks like, this is going to be terrible bread. So bear with me. All right, so then it kind of comes down like this, and it goes over here, and then there's like the bread part over here. It kind of comes around, looks like this. That's not terrible for a loaf of bread. So the idea, I mean, it's pretty bad, but whatever. You draw your own loaf of bread if you think you can do better. The idea here is that in the same way, actually, does anybody know what this is called? The idea of chopping things into small pieces to calculate the total. This is what, it shows up in physics and engineering sometimes. The idea that you can decompose things into small pieces and add up. It actually goes all the way back to Archimedes, right? So this is like ancient Greek in its origin. But the name of it, the name of the idea of taking something and dividing it up into little bits and then adding them up to get an approximation is called Calvari's principle. Okay? And the idea is we could do the same thing to volumes as well. I could take this and say, well, if I could figure out the volume of this piece right here, which totally curved like this, you couldn't tell, but it's there. And then it comes down, and then this piece of bread kind of does this. Back. That if I could compute the volume of each slice, I could decompose the bread, the loaf of bread, into a bunch of slices, compute the volume of each slice, and then add those up, that I get a volume of the entire object, right? The idea here is that if I could compute the sort of volume of slices, and then sum up the volume of the slices, I'm going to be about equal to the volume of the solid.
Area under F and then
Is about equal to area of slices. The idea here is that here, because I'm doing areas, I cut it up into little rectangles that approximate it. Here, I'm chopping this up into little volumes instead. Okay, so how did I do this to myself? Here's one slice of bread, because they're getting stupider every time I draw them. Okay, the idea is that the volume of this, you can always think about as, normally the way you do this when you set it up the first time is you think about this as having some sort of thickness, like say dx. And then you're thinking that it's a cylinder. And so the volume of a cylinder is equal to the area of the base times the width, right? I mean, this is the volume of a cylinder. This you can't tell with the cylinder. All that a cylinder is an object that has cross-sectional face the same as you move through it, right? So this is a cylinder. The volume of the cylinder is equal to base area times width. So the point is that if this was arranged over some domain where you had an x-axis down here that ran from A to B, that one way of thinking about what you're doing is you're saying, oh, well, it's like you're integrating from A to B. Each of these areas dx, right? As you go down this, each one of these is a volume, and you're adding them all up from their location at A all the way to their location at B. Each one of these is like a little volume, and this integral is just adding them up. You like the for loop version of this, it's like the sum from I equals 1 to n of A I delta x. A bunch of little volumes, add it up, and then take the limit so you get the integral off the other side. But each one of these areas can be thought of as also being an integral. How do you find the area under a curve? What do you do with an integral? So if you have something like the integral from A to B of A dx, but this thing itself is determined by this horribly non-convex function that I drew. But imagine here that the distance between this and this was determined by a function f of y, then this too is an integral because areas are also determined by integrals, right? The integral of this is like the integral from c to d of f of y dy. So what Calaveri's principle says is that if you have a complicated object like this, where you have x's that are determining something about how wide or narrow the function is, but for each x value, you've got some relationship between where you start and where you end, then this turns into the area itself is represented by another integral. And it's not just a function of y, it's a function of x and y. Each x position tells you where the slice is. That tells you which particular shape defines the slice of bread. That's the particular curve that you're integrating. The idea with an integrated integral is the first thing you do is figure out the volume of one slice, and the second integral adds up all the slices. Okay, so an iterated integral, the way that you should think about an integrated integral is it's the integral from A to B of some kind of area function that depends on x and y dx. And then this thing itself can be found using one variable function theory. And the reason that it's called iterated is because you have an order to do this in. An iterated integral is do this integral first to find the area, then do the second integral to find the volume. Okay? Yep. Yeah. This is supposed to be a dy. I guess I leave it over there too. Now, the integrals I've written down here are really straightforward because I've implied, by writing A and B and C and D here, I've implied that these integrals have been taken over a rectangle of the domain. Right? This iterated integral is an integral over a rectangle. So you imagine you're in the XY plane, you have an A, you have a B, you have a C, you have a D. This region right here is sort of what lies underneath whatever it is that you're integrating. So the integral from A to B, integral C to D, X, Y, Y dx. One of the first theorems that you learn is that if you're dealing with these rectangular pieces, these are the simplest possible domains. And one of the easiest things to do in calculus that is illegal is to switch the integrals without knowing you're allowed to do it. This is one of the most complicated problems in all of analysis, is when you're allowed to switch the order of integration of problem. And it's the sort of thing that in earlier classes you just wave your hands at. And we're going to do a little bit of that in here too. Those of you that have gotten to the end of the I know there's a couple of people in here in the 412, 413, 414 series. Switching order of integration is controlled by something called Houdini's theorem, which we're going to see in here a little bit. But the idea is that you are allowed to switch the order of these when these are integrated over a rectangular region. For an iterated integral, it does not matter what order you do them in. Okay? This kind of integrated integral over a rectangle. But this is okay. Essentially what you're saying is you could have sliced the bread in the other direction and done the same thing. Okay? All right. Yep. Was that a question, Andre? Okay, none of this should be unfamiliar to you. I'll do a quick example here because, like, why not? Integral, just to remind you, 2 to the 4 x squared plus y 2y dx. So, in the absence of parentheses, you always work like this. Remember that when you're computing antiderivatives with respect to one variable, the other variable is treated as a constant. So that this is the integral from 1 to 2 of x squared y plus 1/2 y squared evaluated from 2 to 4. Don't lose track of what you're doing when you do this. I'm only going to do one of these because this is, I don't find this particularly exciting. I can't imagine many of you do either. When you're doing this, and we're going to be doing some integration in here, the point that I'm trying to make by doing this is make sure that you remember which variable is which. These are dy integrals. So the limits of integration here are y limits. They have to be plugged into y variables, right? When you're done doing an integrated integral at one step, that variable should be gone. So this is what? 4x squared plus 8 minus, put the 2 in there and you get 2x squared plus 2, I believe. This is 2x squared minus 6 dx. And I'll leave it from there. At that point, I think you guys can probably handle it, right? If I've done this correctly. But the idea is when you do an iterated integral, that this first integral eats all of the variable you've integrated with respect to. The definite integral, it gets eaten. Make sure you don't lose track of what's going on here. And no one in here is, this shouldn't be surprising or new to anybody that this is the way you do this. And it reduces to one variable case. Okay, that's all I want to say about 5.1, which is the idea of slicing that you guys learned 241. If there are any questions about this technique, I can answer before I go on. This is just putting our feet down on ground before we go on to something more interesting. All right? Everyone cool? If you're not cool, or okay, actually, here's a quick test. What's that? Yes. Do this by parts, right? Do you have to remember how to integrate by parts? It would be helpful. You did take that at some point. Yeah, this is equal to x log x minus x plus c. logs come up in practice, you should know how to integrate them, right? I'm mostly just playing around with this, but you know, you have to know how to integrate. Okay, so the next thing that we want to talk about, and a thing that is absolutely going to make you think that we're doing the same thing over again. Now, instead of talking about iterated integrals, we're going to talk about double integral. Okay, a double integral is not the same as an iterated integral. There's still two integration signs. But remember, the whole approach with iterated integrals was to think of slicing in one direction and then adding up the slices, right? That is not the way we think when we're thinking of a double integral. And this is meaningful in physical applications. These are different ideas. Iterated integrals have to do with adding up areas of slices, adding up volumes of slices. The way we think of a double integral is like this. If I write a double integral over some region R of some function f dA, this has a different interpretation than that does. I don't want you to think of this as being you slice one way and then you slice the other and add. Not because, I mean, it's going to turn out to be the case that these can often be computed with that way, but fundamentally what we're dealing with here is a different kind of object. The idea is, and the hint is this dA right here. So dA means a small area. So what you're doing is, you've got some region that you're integrating over. And you think about the surface as living on top of it, right? So this is a double integral. So this is going to be a function of two variables. And so living over the top of R is some surface. You know, the two-dimensional picture might look like you've got some sort of sheet up here, and the image of the sheet down here is some kind of blob in R2. So this is f of x and y. And this is R down here in the XY plane. Okay. So I'm just looking at the domain here. To say dA is to say not cut this thing into slices, but imagine cutting this into lots and lots of small rectangles. They don't all have to be the same size. You just cut them up, rectangles everywhere. Each one of these you think about as being a small amount of area. This is the way that a numerical analyst or somebody working as an applied mathematician thinks about what integration is. They think, cut the domain up into rectangles, evaluate the function on each one of these rectangles with some test point. Pick some points in here and figure out what the heights of the function are. Then what you do is, it's sort of like what you're doing here is you're cutting up your surface into these sort of rectangular bits. I don't even know what to call these. Rectangular parallelepipeds. There you go. I can actually draw these in a sort of beautiful way. So you can imagine that, like, this would be easier if I just had a picture to show you, I guess. The idea is I want you to think is a bunch of like blocks that you stack up, right? They're volumes. You're taking the surface and you're replacing the volume that this surface shapes out with a bunch of blocks that have these as the base. Okay? So they're not slices. In fact, it's going to be quite striking theorem when we can turn this into a slices picture. This is sort of a decomposition into little blocks. And the volumes of the blocks are what add up to the volume of the surface. So intrinsically, this thing right here, what this is doing is it's adding up the volume of blocks with small rectangular bases. And when I say numerics here, what I mean is one way of thinking about how to approximate volume is you say, well, cut the bottom up into a bunch of blocks, pick some test points and calculate the heights, and that's actually how you construct the blocks would be. There's the area of the base. The volume of the block here is going to be this area times the height of the function, which you can think of as being f of x and y. That's a small volume. And each one of these represents a small volume. In a numerical analyst, this is what numerical integration is. You cut the domain up into reasonable sized pieces, you test a couple of points, and you approximate. The smaller you make the rectangles, the better your approximation you get. Okay? So double integrals represent the decomposition of the domain of the function into small pieces. Okay, so have I done a reasonable job of trying to explain why those are different? I mean, it matters because this interpretation is like intrinsically physical. When you start thinking about physical applications and how this math gets used, the double integral representation of thinking of the domain as cut into small areas matters a lot. A lot of physical processes don't map onto things where, I'm going to put it over here. This idea where you go from A to B and from C to D of f of x, y, dy, dx, this is the slicing argument where you take some shape and you cut it into thin slices where you compute each slice first and then you add up all the slices by running down it. This is a different approach to the problem than this is. Okay. How do I know these exist? When do they exist? That's one of the things, right? I mean, just because I say that's how you do it doesn't mean that you can. I don't even know when I can do this. What sorts of things am I allowed to integrate? Closed surfaces? I don't even know what that means. What do you mean closed surface? So so it's continuous is the condition that you want. So it's actually easier to integrate than, so you spend your entire life, until you take analysis, you spend your entire life thinking the differentiation is easier than integration. But it turns out that in theory, you can basically integrate anything. And differentiation is actually quite hard. So the first big idea of vector integral calculus is to figure out when I'm even allowed to do this. When do I know that this volume is well defined? And it turns out to be the case that if we're careful about the domain that we're integrating over. So if R is a rectangle, if you're real careful, if R is a rectangle and F is continuous on R, then this thing exists. The name for an integral existing is integrable, right? This says that f is an integrable function. But that's really restrictive. R is a rectangle. Continuity isn't much of a condition. So the big deal theorem is just in the same way. Now I spent all this time telling you that iterated integration was not the same as integration over a region. I'm going to tell you that they are the same in this special case. So one of the most useful, okay, now, if anybody in here has taken Fubini's theorem in any sort of 412, 413, 413 class, you're not allowed to complain about this version of it. This still is Fubini's theorem in an extremely special case. Okay, so what Fubini's theorem says, you don't actually need to know the name Fubini's theorem, but if you could be armed to the teeth with exotic names of dead Italians who have done your math for you, then you should know the names of theorems, right? Impress your grandma. I'm going to switch the order of integrals, grandma. Fubini's theorem says I'm allowed to. All right, so what this version of Fubini's theorem says is that if f is bounded. Bounded. Okay, now why bounded? Well, I don't want to have an asymptote somewhere where the function runs away, right? The function could be continuous on a rectangle, but then like there could be an asymptote on the edge of the rectangle where the function is just sailing away to infinity. I wouldn't want to try to integrate that, right? So if f is bounded on a rectangle. R is equal to AB. Okay, so this symbol AB cross CD just means the picture that I drew here, A, B, C, D, this rectangle. The name of that thing is AB cross CD. If you like, it's the Cartesian product of the points that are contained in it's the Cartesian product of the intervals. If F is bounded on this rectangle and the set of discontinuities of F has 0 area, I'll talk about what that means in a second. Then, after I've long-wittedly told you they were not the same, in this case they are. The double integral over R of F dA, that is the picture where we cut it up into rectangles, can be computed in either direction by doing from A to B and C to D of F of X, Y, dy, dx. Or if it's more convenient, I could go from C to D, A to B of F of X, Y, dx, dy. So the basic idea here is that I want to allow it to be the case that the function is piecewise defined. Right? So when I say the set of discontinuities has 0 area, those of you that take measures, it's like saying this discontinuity is the set of measures 0. Biggest idea here is essentially that any places where F takes a jump is defined by a curve or a line. F is defined someplace, then there's a cut and it jumps up someplace else. So it's mostly continuous. So bounded and set of discontinuities has area 0. If you don't want to remember exotic conditions, just remember continuous. A continuous function allows you to do it. Well, the way a mathematician would write like a bunch of like technical conditions like this is they would say, oh, as long as F is nice, for an appropriate definition of nice. What I want you to remember about this theorem is not the condition about the discontinuities, but essentially that if F is piecewise continuous, on the closed rectangle from AB and CD, then you can do this. The integral of F dA can be computed in either order. This is what I mean by nice enough. Piecewise continuous is a nice enough version of what F can do. Okay? And this is a pretty useful fact because it means that this sort of physical intuition that we get about cutting a surface up into little tiny rectangles, if I actually want to compute this, normally the way the process works is you come up with this idea from either a physical situation or a description of a surface. But then when you want to compute the thing, you actually have to use a computational formula to do it. So what Fubini's theorem lets you do is work intuitively to write down a double integral and then replace it with an iterated integral that calculates it. Okay? Okay. Now, it may not seem like a big deal, but it is. Now, unfortunately, we've got to talk about. Okay, so if I say an elementary region of type 1, does that ring a bell to anybody? Does that mean anything? Depends on what your professor would have taught you. So the idea is rectangles are really restricted, right? A lot of times we want to integrate a function over a region that's not a rectangle. So the big question is, well, what about not rectangles? What about not rectangles? Like, for example, what if I had a domain that looked like this? Say this was f of x, this was g of x, and I said, I'd really like to know what happens to a function defined between those two curves, right? That's not a rectangle. This domain, that's not a rectangle. Or, I don't know, this. That's not a rectangle. I mean, it is if you look at it in a certain way, but it's not a rectangle. You don't believe me, but it is. That's a rectangle. Just, you know, change coordinates. This is not hopefully not surprising. This is not a rectangle. Yep. Well, there's things that are not. This is not a linear change of coordinates, so it's not a rectangle. If you're in complex numbers, everything is a rectangle.
Yeah, I mean, it's actually not true. I mean, it's a circle.
Okay. So of course, that means like if I wrote down a really natural question, like, what is this? Double integral over just this region right here. Here's a region D. Suppose D is given by x squared plus y squared is less than or equal to 1. It's a unit circle, right? The unit disk. I say, I would like to integrate the paraboloid x squared plus y squared dA over D, where D is the region x squared plus y squared is less than or equal to 1. How on earth am I going to get this turned into something that I can use my rectangle theory on? Or is it even allowed to do that? I mean, rectangles are easy to work with. Something like this, not so much. Anybody here fresh out of 241? Anybody remember any of 241 at all? Yeah. Anybody here want to tell me how to do this? Yeah. Oh, yes, but not yet. We're saving polar coordinates until we get to, yeah, I mean, this is the natural way to think about this is a polar coordinates change of variables. I have deliberately not told you about change of variables until we can do it for real. So change of variables, we're going to do double, triple integrals, and then we'll talk about change of variables. Anybody else? So yes, but not yet. But even you change of variables requires thinking about this in a different way. Who else? Anybody else? Yeah. Okay, so what you want to do is say, okay, here's one idea. You could say, well, this function up here is sort of defined as the square root of 1 minus x squared. And this function down here, that's the function minus the square root of 1 minus x squared. So what you're trying to do is turn this into an iterated integral where you're saying, well, what if you pick the x value and you put it back into the strip mode argument where you say, look, every x gives you a band of y values to use. So integrate over the y values first between a top function and a bottom function, and then integrate all the x values that came out. I think you can use the y value. Okay, so the idea is that these are examples, the idea of splitting this into functions and working with it are examples of something that we're going to call elementary regions. So an elementary region looks like this. So y equals b, y equals a, and then some kind of function here that defines the edges. So like a g1 of y, and a, sorry, g1 of x. I can actually define this. Let me make sure I'm not like totally on my own butt here. That was a rude thing to say. X is equal to y, and x is equal to h of y. So a region where you have straight sides on the top and bottom and curved sides on the sides is going to be one kind of elementary region. G of y and h of y. Another kind of elementary region is going to look like this, where you have an x is equal to a, and an x is equal to b, and y is equal to f of x, and y is equal to g of x. So these are both considered elementary regions. So they're not quite rectangles, but they have two sides that are sort of rectangular looking. Okay, so this one, I'm going to make sure I'm using the book's nomenclature here. They call this one type 1. I have no idea why it matters what the classification is. They call that one type 1. They call this one type 2. And it's type 3 if it's both type 1 and type 2. So the idea that we want to use is that once we have the idea of type 1 and type 2 regions, we get a theorem that says that we can do exactly what Jack was suggesting, which is that we can take a double integral over D of f dA, and if we're in a type 1 region, so the type 1 region, here, if the D happens to be x is equal to A, x is equal to B, and you had a y is equal to f of x, and a y is equal to g of x, defining the top and bottom of the region, that if this was the region you were working with, where you had rectangular sides A and B, that you could actually integrate this from x is equal to A, x is equal to B, and then integrate, once you pick an x value, you basically integrate from the bottom to the top. Y is equal to g of x, y is equal to f of x, here should be f and g, y. But be careful, this first integral is a dy integral, and the second integral is a dx integral. These are not integrals that you can reverse the direction of. I know that looks like dy and dx. So what is actually going on when you're doing this? This is an example of an iterated integral where now we're using the fact that we've got a function defining the top and bottom to build up this sort of Cavalieri strip again, right? This gives us an area, and then we're integrating all those areas together to get a volume, okay? So the idea is, in this sort of region, a double integral can be reduced to this kind of iterated integral. So in the example that we gave, where we had the double integral over d of x squared plus y squared dA, where the disk we were working with looked like x squared plus y squared is less than or equal to 1, that would have been the integral from -1 to 1 of the integral from minus the square root of 1 minus x squared to plus the square root of 1 plus x squared of x squared plus y squared dy. Yes, that's where I'm thinking of that circle as being broken into a function that looks like